Good evening, everyone, and welcome to this special session organized by School of AI Algiers. Tonight, we're excited to dive into a brief history of natural language processing, a fascinating journey through how machines have learned to understand human language. We're honored to have with us Amine Abdaoui, Senior Applied Scientist at Oracle, who brings deep expertise in AI and NLP. His works bridges research and real-world applications, and we're grateful he's here to share his insights with us. Thank you for joining us live on YouTube. Stay engaged and feel free to ask your questions during the talk. We'll be more than honored to answer them by the end of this session. Please give a warm welcome to Amine Abdaoui. Amine, the floor is yours.
Thank you. Barakallahu fik, Nawal. Thank you, first of all, thank you for the invitation, School of AI. حبيت نكون معاكم avant من قبل ولكن الحمد لله ça s'est fait هذا العام. Donc merci pour la présentation. As Nawal said, my name is Amine Abdaoui. I am a senior scientist at Oracle. I have been working on natural language processing for the past 12 years. So I have seen the field evolving from, let's say, standard machine learning when I started to more clever models and techniques, especially using self-supervised learning, and then for the past maybe 5 years with a big hype around large language models. So in today's presentation, I will give a quick overview of how the field has evolved over the past 10, maybe 20 years. I will not specifically talk about the fancy things that we can do with LLMs, but I will rather focus on how these models are built and what are the core architectures and ideas behind this kind of models. Okay, so I will mainly speak in English, but I may switch to French or to Darija, as I may have done already. And if you have a preference, so please let me know. I can switch or explain whatever you want. Okay, so the plan of the presentation is here. So I will first talk about text representation, which is an important and big topic in when dealing with language, because a language by nature is unstructured. So we have when we talk about natural language processing, we are usually talking about text. Audio speech is another type of input, but mainly when we talk about natural language processing, we talk about text, and text is not numbers, so we don't know how to manipulate it or how to use statistical models or mathematical models on such unstructured data, and how we can represent the text can have a big impact on the models later. So we will talk about text representation briefly, and then we will talk about. So I will first show how we were doing natural language processing using previous text representation methods, and then more recent ones, and how we switched to attention and transformers. So I will, of course, talk about attention and transformers, how we train them, how we fine-tune them, how we make them capable of following instructions, and what happened, why the field has gained a lot of attention in the past 5 years, and what happened specifically since 2021 maybe, or 2022. Why the current models are really doing much better than what we had before. Okay, so I used to use this slide in the beginning of my presentations earlier, several years ago, because there were a lot of attention towards other types of data, like images. Deep learning was first successful on other types of data, so as I said, mainly images. And language was kind of a complex or difficult type of input, and we thought that we are not there yet. So 10 years ago, or maybe 15 years ago, if you talk about machine learning, you will probably hear things about ImageNet, and not a lot of things about text. So I used to have this slide to show the relationship between language, understanding language, and AI. And this slide shows actually the Turing test that was published in the 50s, in the 1950s, so many years ago, by Alan Turing. And by that time, the test he made to decide whether a machine is intelligent or not, actually the criteria that he took is whether a machine can understand and communicate with the human language. I can recall the test very quickly. Sorry about that. So I can recall the test very quickly. So the idea of Turing is to put evaluator C in front of two agents, A and B. One of the two agents is a machine and the other one is a human. And the evaluator doesn't know who is the machine and who is the human. He is asked to decide which agent is the machine and which agent is the human, only based on textual interactions. So even by that time, the idea of making machine capable of understanding and generating and interacting with the human language was the main criteria to decide whether a machine is intelligent or not. Okay, so we will start now with text representation. So the standard way of representing unstructured text data 15 or 20 years ago was what we call bag of words. And the idea is to take some unstructured data that can be emails or Wikipedia pages or news or anything that contains text, and to represent it in a numerical form, a matrix, where the line will represent the documents, the individual emails, documents, or web pages will represent the rows of this matrix, and the columns will represent sorry, what we call tokens, which might be words or subwords that are that exist in our textual data. And then the matrix will be filled either with Boolean information, with zeros and one, for example, saying that this token or this word appears in this document, so we will put one, or it doesn't appear, we will put zero. And we can also have more intelligent, slightly more intelligent representation by putting frequencies or TF-IDF, any other numerical form that helps us transform our unstructured text data to some numbers that we can then feed to standard machine learning models like decision trees, SVMs, or even neural networks that by that time were not as complex as today. And we can train our model that, for example, can classify our documents into categories. For example, news web pages into categories health, sports, or if I have emails and I want to know whether this is spam or not. So I can train a standard machine learning model on this bag of words representation. Sorry. The problem with this representation is that we are not including the meaning of the words. We are not giving importance to the meaning of the words. We are dealing with the words individually, or with the tokens individually. For example, if I have a word, three words, car, vehicle, and banana, I know that car and vehicle are semantically close. So the distance in meaning between car and vehicle should be closer or smaller than between car and banana, because banana is a fruit. So, however, with this representation, these three documents have exactly, or these three words have exactly the same distance between them. So a document containing car and another one containing vehicle will be as different as one containing car and another one containing banana. So this is why in 2013 a new way of representing text data was proposed by Thomas Mikolov, who was working at Google by that time, and a lot of the work that I will be showing was published by authors who worked at that time at Google. And his idea is to represent each word with a vector of n dimensions. And this vector will somehow encapsulate or contain the meaning of this word. So the final word embeddings, I will talk about how we can get them. But the final word embeddings that we will get, if we project them on only 2 dimensions, of course, we can have more than 2 dimensions. We usually have hundreds of dimensions or thousands with the new LLMs. But if you project them on 2 dimensions, we will see that car and vehicle, we will have close embedding, so we will be close, and banana and apple, because these are fruits, will be close, and we can even have more interesting observations that the distance between the female version of a word and the male version of the word will be always almost similar. Okay, so the question is how we can get this kind of word embeddings. The idea of Thomas Mikolov is to use raw text data, and he proposed 2 architectures that we can use on raw text data, so just text, to learn those embeddings. These 2 architectures are very simple neural networks, and the idea behind this method of getting the word embeddings is to detect or derive the meaning of the word using its context. So what the task will be to train these word embeddings is to use the surrounding words of a given word and try to predict the current words using the surrounding words. And this is actually something that is that us as a human we can do. Even if I don't know the meaning of a given word, I can deduct its meaning using where it is used. So, for example, if I say I took a cup of coffee this morning, and later, so I know the meaning of this word, of all these words in this sentence, and later I will see I took a cup of tea. Even if I don't know the meaning of tea, since it is used in the context I took a cup of, I will know that this is something that I can put into a cup, that I can take, drink, and I will deduce that tea and coffee are somehow similar because they are used in similar contexts. And this is actually a first shift because starting from here, we are not only training our model based on the data we have. For example, I talked here about training a model that detects whether an email is a spam or not. So if I train this way, I will only use emails that are already annotated, labeled with spam and not spam, to train my model. Starting from here, we were already doing transfer learning because these words embeddings are trained beforehand on a lot of text data that is unlabeled. I don't need any labels, I just need text. And I will try to train these words embeddings that capture the meaning of the words before training the model. And then typically the models we were using, let's say just after the Thomas Mikolov paper, let's say 10 years ago, were most of the time recurrent neural networks because of the nature of text. Text is sequential. We have sequential data, so these recurrent neural networks are well adapted to sequential data. So we will start with pre-trained word embeddings that we trained before using Thomas Mikolov method. And usually they were existing, like we can download pre-trained word embeddings from Glove, Stanford, or any other lab or people who already trained word embeddings. And then we will put on top an LSTM, or a recurrent neural network, that will that will consume the word embedding sequentially. And then we will end up with a final LSTM representation that we will use as a representation for the whole sentence. So if I have a sentence, Apple is a good company, I will I will start with word embeddings, I will add my LSTM units, and I will end up with a representation which is actually the final representation given by the last LSTM unit. And this representation will be a vector that represents my whole sentence. On top of that, I can do a classifier, a simple fully connected layer, and I can get what I want. For example, if I want to classify sentences according to their sentiment or opinion or emotion, I will add a classifier and I will train my model to predict the sentiment expressed in this sentence. This was already better than training a bag of words model with a standard machine learning model like SVM or random forest, but this architecture also has issues. The first one is that LSTMs or recurrent neural networks in general are slow, because we cannot do a lot of parallel computation. We really need to compute the first LSTM unit, have its output before being able to compute the second, and so on. The third one will also depend on the output of the second one, so we cannot do parallel computation. We really need to do this sequentially, so this takes time. We cannot benefit from the current processing units that can do a lot of parallel computation. The second the second problem that we had with this architecture is that since we are ending up with only one representation that is coming from the last LSTM unit, if I have too long document, my model might forget about what has been said in the beginning. So one embedding for long documents is not very good, especially with LSTMs or with recurrent neural networks in general. And the last and biggest problem is the context. So it is great that I now start from word embeddings that already encapsulate the meaning of the words, but a given word may have different meanings in different contexts. So if I train only one embedding for every word or token, so Apple, for example, will always will have one static embedding, then I will have the same embedding for the two meanings of the word Apple, both the company and the fruit. And this is problematic because since the only thing that I am taking into account here is the static word embedding, I am not doing any contextualization later before my model. So I don't know whether the current context is the fruit or the company. So a few years later, in 2017, a paper came out from Google again, talking about a new architecture that is purely based on attention mechanism. And this new architecture actually resolved the three problems I mentioned here. And in the paper, the authors tried it on a task. It was a machine translation task, and they showed that actually only this architecture that uses only self-attention, as we will see, attention, that only uses attention, is enough. We do not really need, gives better results than other models using recurrent neural networks or convolutional neural networks. So before talking about transformers, I will quickly talk about attention. So attention was proposed not in this paper, because attention was proposed a couple of years back in 2015 in Benju team in the context of machine translation also. So I am using here the example is not machine translation but classification, but the idea is the same. And it was proposed to avoid this problem of relying only on the last representation. So the idea of attention is that instead of taking into account only the last output of the LSTM here, for example, I will take all the outputs of all the LSTM units, and I will weight each output with an attention weight. So if I have a word that is important for my task, it will automatically, the model will automatically learn to give it a high attention weight. For example, if I am doing sentiment classification, and if I have the sentence, Apple is a good company, I know that the word good is important for sentiment classification, because I know that this is positive, this is something positive, not negative. So the model will give this word a higher attention weight. So when I will create the representation of my sentence, this word will receive higher attention. Now, these attention weights, we do not learn a model that gives static attention weights for each position. These attention weights are actually dependent on the input. And how we get them? We usually use a small neural network that calculates these attention weights from the input. So we will have this small layer that takes into account the different LSTM outputs, produce the different weights to say that, okay, Apple is not important here for my task, because it will be learned. So this neural network, or small part of the neural network, will be also learned. It will learn that is, okay, here also is not important, but good is an important information for my task. And then I will be able to do my weighted sum, to have my sentence representation that takes into account all the words and will also give more importance to important words for my task. So going from attention to self-attention, so the idea in the transformer architecture, and we will talk about that in the next slide, is the same way we were doing attention between the task and the different words, or in the paper that introduced this from Benju team that was doing machine translation from English to French, for example, then having the ability to calculate attention weights between each output token and each input token or input word is interesting, because sometimes when you translate, this is also important for translation, because when you translate, you may not have the same order in the different language. So it is always good that you allow each token to go back into the inputs and calculate its own attention weights to see where are the important words that I should use in order to make my prediction. the idea in the transformer architecture is to do attention between the same input. So if the input and the output are the same, then the attention weights that we will be computing are called self-attention. And the idea of this self-attention is that when I have a word, I may start from a static embedding, but I will look around, look at all the other words in my documents, and try to see if there are words that can help me contextualize myself, or give a more accurate representation or more accurate embedding. If I take the example of Apple, so I might start with one embedding for Apple, and then if I use self-attention, I can look at the other words and see the context. If the context is talking about the company, then I will adapt my embedding to be to reflect the company. If the context is talking about the fruit, then I will adapt the embedding to the fruit. So the idea of self-attention is mainly to contextualize the representations. So here on the left, I am showing the architecture proposed in the Attention is All You Need paper, which is purely based on attention, as we said. So we have two blocks. The encoders block, we have a set of encoders, and the decoder block, a set of decoders. And if you look inside, you will see that, okay, I have text, I have input embeddings. I will transform my text into tokens. Each token has an embedding. I will add positional encoding. And then all the operations happening inside are either self-attention or simple feed-forward or layers, or just normalization, addition, this kind of operations. So I do not have any recurrence. The whole input will be handled at once. I do not depend on on other units. The only thing in this architecture is that I have to compute all the encoder steps before computing the decoder steps, the decoder operations. But apart from that, anything inside the encoder and anything inside the decoder happens at once. And if we look at the encoder, for example, so as we see here, we have a multi-head self-attention. So we have self-attention feed-forward in each encoder block. Each encoder block is taking into as input embeddings and producing embeddings. And as I said, the idea is that I can start from static embeddings, as the word embeddings we were training with Word2Vec. But then each self-attention computation happening in each encoder block will contextualize these embeddings. So we will end up with the same embeddings, the same dimension, but these new embeddings are contextualized. So, and this is the first advantage of the transformer architecture, is being able to use self-attention to change the embedding of every word according to the other words that are here. So Apple will have different representations in different sentences, in different contexts. The other advantage is speed, because we can, as I said, we can do parallel computation. So here, I will show this in the next slide. We talk about multi-head self-attention because we have several attention heads, and each one is doing its computation independently from the other ones. And as we have seen on the Attention is All You Need paper, and then a lot of work, that this architecture actually works and gives us best results. So we can rely on it and do not need recurrence or convolution. I will briefly show the details of the computations happening inside each multi-head attention here. So let's say that my encoder layer, or even decoder, so in decoder we also have cross attention, but the mechanism is the same. So in each decoder block, we'll receive embeddings. Here I have two embeddings because I have only two words as input, thinking machines. So this is my input. I start from static embeddings that are already computed. I have an embedding for thinking, a set of values for the word thinking, and a set of values for the word machines. And then, sorry, inside each encoder block, I will have model weights. The attention here is using three matrices actually that are combined in some way to get the attention weights. So I will use the model parameters that are learned to get what we call query key and value matrices from my input. And then I will use a specific formula that is detailed here to calculate the attention weights and then to get the contextualized representation. And this operation is happening over several heads. So same thing is happening here, same thing is happening here. And each one is doing its computation independently from the other ones. So we can do parallel computation here. So this, even if we are doing maybe more operations, this can be done faster using current processing units. And I'm here showing so I took this from this figure from the J.L. Ammar blog, Illustrated Transformer. So you can go there and you can actually understand every operation, intuition behind every block here, and how actually transformers work from the input to the output. Okay, now the transformer architecture was proposed in 2017 in the Attention is All You Need paper. But actually, we had to wait until 2018, 2019, the paper was published, to have the first pre-trained language model that uses the transformer architecture. Because what the Attention is All You Need guys did is just propose the architecture, use it for a given task, only one task, which was machine translation, and that's it. They didn't release any pre-trained model that we can use, and they didn't push a lot the idea of self-supervised learning, where we can actually rely on pre-trained, rely on raw text data and pre-train something that can be used for different tasks. And this idea was actually proposed in BERT, which was BERT, so the first pre-trained transformer-based language model, and which was also published by Google guys. By that time, Jacob Devlin, I think he left. And what he used, he only used the encoder part because he didn't wanted to use the decoder. The decoder is good for generating text, predicting tokens. The encoder is good for understanding text. And by that time, most of the tasks that we were dealing with when talking about natural language processing were natural language understanding tasks. Meaning that I have a text, I want to understand what is inside, and do one thing. I can do sentiment classification. I can tell you whether the sentiment expressed here is positive or negative. I can give you the category. I can tell you whether this email is spam or not. But the idea of generation was not exists. I will talk about that in the next slides. But most of the work that we were doing in natural language processing was, or at least the most interesting work, was on natural language understanding tasks. So BERT was a natural language understanding model, but it was pre-trained model, meaning that the guys took the transformer architecture and they trained it on all Wikipedia. How they trained it on all Wikipedia, because Wikipedia is just text. They did a similar idea to Thomas Mikolov. So also they use also a self-supervised task. When we talk about self-supervised tasks, these are tasks where we do not really need labels. We use only the raw text as label. And their idea, they use two objectives. And the main one is the masked language modeling. The idea of this task is to mask one word randomly in the sentence or a set of words, and then try to predict it using the other words. So if I mask the word that is here, the word is, and then I ask the model, okay, based on the other words, Apple, a great company, what should be the word here? So the model in the beginning will not be good, but since we are training it to predict the good tokens each time, so it will learn actually to predict the good token. And by learning to predict the good word or token at this position, it will learn the meaning of the words. It will learn the language, basically. I don't know if you remember, but when I was in primary school, this was masking a word and asking us to complete this word here was one of the exercises our teachers used to give us in order to be able to understand the language, basically. And here, this is the idea is similar, but we are training the model again. We are training the model to predict the masked words, and by doing that, we are training the model to learn the language actually. So BERT was released, and it was the first pre-trained language model using the transformer architecture that other people started using, because actually when you have, I will talk about that later. Because when you have, I will go here. When you have the BERT model, you can do things on top. You can classify the opinion, you can classify the sentiment, the spam, and you can, here I am showing a more complex architecture on top of BERT to extract relations expressed in a sentence. I will talk about that later. But let's go back to here. So, BERT was a transformer-based language model. They only took the encoder part because they were interested in natural language understanding tasks, and they trained different models with different sizes, hundreds of millions. This was the by that time the common model size, millions. Now, I think you all know that now we are using billion parameters models. But what I want to say in this slide is that where Google trying to train an encoder-based model, OpenAI was training GPTs. And GPTs, the idea is very simple. They were just interested in the decoder part, because what OpenAI was doing by that time in 2018 is to train language models that predict the next token. And by predicting the next token, so each time if I predict the next word, I will end up with generating a whole sentence, document, or even if the context is very long, I can generate books. And there were other works that tried the whole architecture as a whole, as T5, BART, also with an A, B-A-R-T, are pre-trained models that are trained on raw text using self-supervised learning objectives, but they use the whole architecture with both encoders and decoders. So as I said, by that time, 2019, 2020, most of the interest was around BERT, because we were all doing natural language understanding tasks and having a model that was pre-trained on a large amount of text, or Wikipedia, and even later it was trained on more text than Wikipedia. And using it for your own task, for the classification task you are using, it will give you very good results. So a lot of people were working on that, and we have seen a lot of work to train a BERT-like architecture, a transformer encoder, or for a given language. So for example, we had Camembert, which is a language model similar to BERT, but trained for French. This was Facebook AI Paris who trained it. We had also a BERT version for Arabic, trained by Wissam El Antoun, he's now working in INRIA here in France, but by that time he was in Lebanon. And we worked on training a BERT-based language model for the Algerian dialect, which we call the Dziri BERT. So once we have these pre-trained language models, the original BERT, and then many other BERT versions, Roberta, that were either specialized for given language or dialect, or trained on much more text, trained longer also, like Roberta. And then we used those models to do natural language understanding tasks. So we were doing the same tasks we were doing before. We were just much more efficient. We were having much better results. So we were doing classification. We were doing relation extraction. So if inside the sentence I find a sentence that say Oracle filed a lawsuit against I don't know which other company, so I should detect that a lawsuit was here. Or if I see a sentence that says that Oracle buys H100 GPUs from NVIDIA, I will say that I have a client-provider relationship between these two entities. Anyway, just to say that we can do whatever we want on top of that. But the same thing that we were doing. So basically what we had is that we had a model that was pre-trained, and then we will train it, as we were doing before, to do one task. And this task is, as I said, my model classifies emails to say if they are spam or not spam. So it cannot have a chat with me, and it cannot I don't know, find the best restaurant or help me do math, because my model only classifies emails to spam and not spam. I give it text, it says this is spam, this is not spam. What OpenAI has actually changed for us is that they started telling us that the generative models or the decoders, the GPTs that they were training, are actually multitask learners. They can do many things. They can do almost everything we want. They are decoders, they will generate text. You could give them text, they will generate more text. But since they have been trained on a lot more data, they can be useful for much more things. Because before, as I said, we also had this generative models in the past. And the main usage, let's say, business usage that was common for this kind of generative models or decoders is autocomplete. So if you are writing an email or if you are writing something on your phone, you may have suggestions, and these suggestions are usually simple language models, decoder-based language models, and they were very good at that. So predicting what should be the next word once I have a set of words. But things changed when OpenAI trained GPT-3, which was much bigger than what the type of models that we were training before. And they have seen that these models actually are more than that, are more than autocomplete models. They can actually do more complicated things, and I will be talking about that in this section. I think I talked a lot, but I will do the rest quickly. I do not have a lot of slides. So here we come to the large language models, the hype of the last 5 years or a bit less. So when we talk about large language models, of course we talk about, as I said, models that are much larger than what we were training a few years back. As I said, BERT was 100 million parameters, and GPT-3 is 170 billion. So you can see here I'm showing in this figure the number of parameters. This is the time, the different models that were released, and then you have OpenAI, who trained 175 billion parameters. So you can see the scale in terms of model size, number of parameters. But the thing to remember about large language models is that if you train a much larger model, but you still train it on a small portion of text, you will not use the training capacity of that model. You will end up with a poor model, even if its size is very big. So you have to train a very large model on a lot of training data. So we still train them on text data using the same, at least at the pre-training stage, the same objectives, self-supervised learning on raw text. So basically what we do now is that we collect everything we can, every text we can find, we collect it. People usually say nowadays that we train it on the whole human knowledge. So all the text we produced, the humanity has produced, all the books we have written, or everything on the internet that we can use, we will use it to train our models. So we trained on very large training sets. Okay, so very large model trained on very large training sets, trillions of tokens, and we train it a lot. So like if you bring a lot of training data and you train it quickly, so you will not even do one epoch, so you will not even see the whole data. Doesn't mean anything. So you have to train it for a long time. And if you have these three ingredients, what we call scaling laws, then what OpenAI has seen in the beginning, and what a lot of other companies, a lot of other people who are training large language models see, is that you will have a much more intelligent model that is capable of doing much more things than just to predict the next token and to predict tokens that are, or words that form a reasonably good language. And I will show this paper, who actually shows something that is a bit intriguing even. So because basically when we were training machine learning models, we already knew that if you train bigger models or more data, you will have better models. But we were having accuracy curves that look like this, that it will go up, and then it will calm down a bit. So you will not gain much later. What we have seen with large language models, at least this paper also from Google is saying, is that if you train, here they are showing these numbers represent the amount of training we did. So it combines everything. So the model size, how much we trained it, and the data. And actually, starting from a certain point, the model will acquire new skills. So if you train, when you were training smaller models, they were good as autocomplete. But when you train much larger models on a lot of data and do longer training on huge clusters, a huge number of GPUs, at certain point, the model, certain abilities will emerge. For example, the model is just trying to predict the next token, but it starts to be good on mathematics, arithmetics. So I think here it's addition and subtraction. I'm not sure about multiplication. But okay, if you do 1 + 1 = and then you let the model predict the next token, it's probably that it will predict 2. But quickly, when the arithmetic start to be complicated, models usually are not good at that, not good at mathematics, because they at least before, we were not specifically interested in them doing that, doing other tasks than just predicting the next word. And what we have seen is that when training very large models, the models suddenly start to become really good in other tasks that go actually beyond language, and we started to really to question whether these models are really intelligent or not. Where are they really acquiring intelligence? Which kind of intelligence? And then we are now talking about reasoning and this kind of things. And here we have actually a dilemma. So you have actually two schools of thought now, that you have companies that still want to continue to build larger models, and saying that, okay, our scaling laws is still continue. We train larger models, we still have better, we train larger models on more data, we still have better models. And there is another school that where companies are saying we probably got there, because as I said, you need a lot of training data, and basically we are collecting almost every data we can get today. So if you increase more the model size, you probably don't get enough data to be able to use this full capacity, the full model capacity. Okay, so one last slide. So I have been talking since the beginning of my presentation about self-supervised learning and pre-training, saying that all these models are trained using a self-supervised learning task. For example, masking a word in the case of BERT, or predicting the next word, so masking actually the next word that will be predicted in the case of GPTs, decoders. And this is true. So this is what we do during pre-training. And this is what takes a lot of the most amount of time, cost, and everything, because this is the most the hardest part, at least in terms of long training and cost and so on. But once we have done this pre-training on text only, what OpenAI did is to make this very large language model, such as GPT-3, for example. I know that they have 4 now, but at least by that time, the model that they trained, that they said it is actually a multitask learner, they wanted to give it to the public. And before giving it to the public, it's a bit annoying to give the model to give a model that only predicts the next word without any how can I say that is not capable of having a conversation with you. So what they did is that they fine-tuned that. What a lot of people do today is to fine-tune an already pre-trained model using self-supervised learning, so that it can now follow instructions, it can now answer questions, and give you, it's like the interface that you will access to what the model has learned during its pre-training phase. To get access to it, because you don't want to write very complex prompts and think, how can I get this from the model? They fine-tuned it in a way that when you give it a question, the model should know that the next token should be the start of the answer to your question. So if you give it, if you use GPT-3, for example, and you give it what is the distance between Earth and the Moon, it will, and you ask it to continue, it will probably give you another, for example, another question. What is the distance between Earth and Mars, for example? Because it probably have seen these questions in, I don't know, in an exam, for example. But the ChatGPT, if you go on ChatGPT and you ask it, it will answer you, because it received this fine-tuning phase. So they did 2 kinds of fine-tuning: the supervised fine-tuning that we were already doing before. So supervised fine-tuning means you give it the question, you give it the answer, the response, and then you ask the model, once you have this question, give this answer. But the thing that is innovating is that they introduced a new way of fine-tuning the model through reinforcement learning. And instead of giving it only one answer, there are plenty of questions where you don't only have one correct answer, you may have a lot of possible answers, and one answer is better than the other one. So you can actually use that. So you can sample from the model different answers to your question, and then you will ask an annotator, a human, to label whether this answer is better than this or better than this. And they have seen that actually by training the model on these preferences using reinforcement learning, they actually have a much better model. And thank you for your attention. I think I took more time than expected.
Thank you so much, Amine, for this insightful session. It was really heavy, in terms of informations and so on.
Thank you very much.
So there is some questions in the chat. If you are ready, let's begin with the first one.
Sure.
Okay. So the first question: most students may feel limitations regarding compute needs in NLP research. What is a useful direction for students passionate about contributing to NLP?
I completely understand that. So this is not only a problem for students, even public institutions who do not have enough money can feel intimidated, at least to train this kind of models. But I think that the field is now open to a lot of innovations. So even if you cannot train this kind of model, of course, you can maybe find I don't know, a better way of optimizing the current models or using the current models to do interesting things. So I agree that today it's complicated, or it needs we need a lot of resources to train these kind of models, or even to fine tune them. But I'm sure if you can contribute and if you can build something that is more efficient, everybody will try to use your idea. So this is one part. The other part is maybe to work on the evaluation sets. A lot of people are working on that as well. We want to have good test sets to really evaluate our models. So that's also something that you can work on without having to train, without having a lot of resources.
Okay, so you see, even the idea that the student may bring is interesting, like it's an added value.
Sure. I'm not sure I heard everything you said because it froze at some point. Yeah, but I think you said that even if we build data sets and even if we find an optimization, it can be useful, right?
Yes.
Exactly. So and actually there are a lot of possibilities, and a lot of people are working on the field. Sorry to interrupt you.
I think so.
It's fine. I know.
Okay, so I guess we can move on to the next question.
Sure.
Okay. The next question is: attention presented a remarkable shift in NLP. Is attention now conventionally present the go-to, which continues scaling, or are there research exploring other shifts in?
Yeah, in the NLP, very interesting question. To be honest, everybody is using attention. I still see some papers trying to innovate in terms of architecture. I think there were a paper 3 years ago that tries to use convolutions and that try to bring back convolution in the game. But today everybody is using attention. There are a lot of optimization on how we compute the attention, and a lot of very interesting papers, and also successful because I think the authors got really a lot of citations, a lot of impact on the field. Not the same as the attention is all you need paper, but I have seen papers that try to innovate on how we compute these attention weights more efficiently. I have seen, and even recently, I have seen a paper that tried to replace from Yann Lequin team at Meta, that tried to replace I think the normalization, the layer normalization, with a cheaper operation in the transformer architecture, and this one also got some attention from the community. So there are innovations, especially how to compute the attention weights, such as flash attention, and you have a lot of innovations in that direction. But all the models that I am aware of use the transformer architecture with very slight modifications. We do not hear you. I think you are muted.
Yeah. So thank you very much for your answer. So due to Wi-Fi issues, we lost Nawal. As regarding the question, I believe there are also researchers right now working on something called state space models, where they don't use attention mechanism. They instead use like LST, like the basics or the basic ideas behind LSTM. But what they do, they like parallelize it in order to make it scalable, in order to make it scalable for training and for inference. Yeah. So for the next question asked by Aya bin Ali Khoja, it says, how did the integration of reinforcement learning influence the development of LLMs?
I think this is a lot of people are doing that today, and honestly, I was not at all interested in reinforcement learning until ChatGPT was released. So it seems that it's a game changer. It seems that if you only fine tune using supervised learning, you will not have the same performance that you have with the reinforcement learning, because it's similar to if you do supervised learning and distillation, because if you train only on truth, you say this is correct, this is the question, and this is the right answer, you are really limited. So you do not give a lot of as much information to the model as if you say that, okay, you have these answers, but this one is better than this one. This one is still correct, but it is also better than this one, and this one is the worst. I think you give some nuance to the model that you cannot give it with traditional supervised learning, fine-tuning.
Thank you. So one more question to go, and the question says, what are some research directions regarding the use, experimentation, understanding of LLMs? In other words, research directions that can be explored using inference only for cost efficiency.
Research directions that can be explored using inference only. This is also a very interesting path. There are today already a lot of innovations from the most known ones, quantization, that try to make inference much cheaper. I am also now working on something related to that. Unfortunately, I'm not, I think, allowed to speak about it. But this is an important field. what I can give as ideas. So this is a good direction. So as I said, you can go towards quantization. So what quantization does is that the model is composed by parameters, weights that you train, and then you will apply during inference. Instead of putting them on 32 bits or 16 float 16, for example, which is standard, you will use maybe 8 bits integer or even 4 now. And there are a lot of work in that direction, and actually you can get good results. Other direction, maybe distillation. What distillation does is that you train a smaller model from the bigger one. There is something that I worked on before that is public. So self-attention is actually quadratic to the input, because you compute self-attention weights between each input and each token and each other token. So the more tokens you put, the more it increases quadratically, not linearly, but like an exponential. So what you can do, instead of dealing the whole computing all the self-attention weights for long sequences, you can try to have better ideas. And one idea is simply to cut, and then you put the first attention layer between the first, I don't know, 100 or 1,000 sequence, every 1,000 sequence, and then you combine through other attention layers. There is also the work about sparse attention, where you try only to calculate attention weights with surrounding tokens. But again, I don't know if this person is doing research, but these are complicated. How can I say? Not really complicated, but advanced. It's really great that I'm seeing questions about research questions. I thought that my presentation will be annoying because I will not be showing fancy LLMs. This is what we can do with LLMs. But I'm happy to see these questions, and I would be really happy to see innovations or contributions coming from the audience here.
Yeah, thank you. I guess Nawal can be back.
Yes, I am here. Sorry. So the last question is, could you elaborate on the model scale in terms of training, FLOps, floating point operations?
Well, I am maybe not the best person to talk about that, but in a few words, so we usually quantify. So I was talking in my presentation about 3 things in LLMs: the model size, training set, and training longer training. And actually, you can measure that using floating point operations, because at the end you are doing just usually matrix multiplications of floating points. So you can measure these 3 things, or your training, how much your training costed. You can use that as a measure. Maybe you can, Nawal, you can complement my answer if you have more information to share.
No, I don't have. It
Okay,
was the first time I hear about this word.
Okay, so if you only want a short answer, then yeah, this is a way to measure how much operations we did, for example, during our training, and it will allow us to combine everything actually. Because if you have a bigger model, you will do more operations. If you train it longer, you will do more operations. If you have a bigger training set, you will do more operations.
Okay, thank you. So this was the last question, and that brings us to the end of this session. Valuable knowledge. Can you hear me?
Yes, we hear you.
Okay.
Thank you very much.
And thank you to everyone who joined us live. Your questions and enthusiasm make all the difference. We hope you found this session useful and inspiring. Stay tuned for more events coming from School of AI soon. Until next time, take care and keep learning. Have a great night.
Thank you all. Thank you. Goodbye. خلاص